you if you want to put it in full screen.
Okay, I'll put that one like this. Okay.
Okay, I think we should
Yeah.
be good to go.
Okay.
Okay, that looks good. I'll go ahead and introduce you.
Mhm.
Good afternoon, everybody. Thank you for being here. I'm really excited to introduce our speaker today, Professor Guosheng Liu. He is a professor of meteorology at the Department of Earth, Ocean, and Atmospheric Science at Florida State University. And he has a lot of different specialties that he does, radiative transfer being one, satellite remote sensing as another. And I've been particularly interested in his work for a long time because he has done a ton of work towards the impact of ice and snow and its radiative effects, including scattering, and all that work has gone a long distance in us better understanding retrievals from the CloudSat satellite as well as the GPM satellite. And so I'm really excited to have him as our visitor today. And Professor Liu will be talking about studying cloud ice and snow using satellite observations. So go ahead.
Okay, thank you very much, Claire. Thank you for inviting me to give this talk. And also thank you everybody, in this busy time to come to, to my talk. And today I'm going to talk sort of two separate topic, but all related to the cold stuff, like cloud, ice, and snow. And when they doing, ice and snow, when they go to meetings, people always saying, what the hell are you doing? What the heck are you doing that in Florida, in that warm sunshine place, doing ice and snow? I always answer, I really don't know either. So just end up this way. So today, I'm going to talk two topics here. One is how the cloud ice radiative effect, basically how the cloud ice will either warm the earth or cooling the earth, based on observation and numerical simulations. Another one I'll spend maybe a little more time on is doing the partitioning of liquid and solid precipitation. And that part is ongoing research. I still have lots of things in the research, have lots of things not really fixed, or still have lots of problems I need to solve. So, so that part, maybe spend a little more time on that. First of all, let's say, what's the cloud ice radiative effect? So this one, basically, it's sort of long, a question sort of written in the textbooks. It's from many years ago. Basically, we know the cloud ice cloud, or whatever you say. You have the two basic effect. The first one is they intercept or reflect some solar radiation, so that they sort of cooling the earth, because the solar radiation cannot come in. So we call that albedo effect. And another one is the cloud will intercept the radiation from the surface and then re-emit the radiation, long-wave radiation to the space in a lower temperature, so that it's working like a greenhouse. So we call that greenhouse effect. And whether the cloud will warm the earth or cooling the earth will depend on the balance of the two effects. For most of the water clouds, basically the albedo effect is much larger than the greenhouse effect, so that most of the water clouds, you can safely think they're sort of cooling the earth. Because the more cloud there, the earth is less radiation, basically cooling the whole thing. But the ice cloud depends where you put the clouds, how thick the ice cloud are. Then they have the different effect. That's why I'm interested to look at how the ice cloud are acting to the radiation. So there's many previous studies and some of the studies, actually biofaculty from your department, doing a whole lot of that. Is Tristan actually, and the colleagues did lots of work on that. If I click this, it can should show up a result, say is different type of cloud. You have the effect. Globally, you have either warm or cold to the Earth, cooling the Earth or warming the Earth, depending on what kind of cloud, what type of clouds are. And also some other studies basically focus on the cirrus cloud, basically the thin one, the thin clouds, saying how much they are cooling or warming the Earth. And also there are studies to focus on the different locations, say in the tropics or in the monsoon region, how that works. So our question here is that something like this. Say if you're using observations, you globally average everything together. What type of clouds, or you say what's the optical depth? What the optical depth will be, the separating the cloud that warm or cooled Earth. Basically, we're trying to find a sort of threshold, globally averaged one threshold. So beyond that threshold, the thicker ice cloud will cool the Earth. The warmer ones, the thinner ones will cool the Earth. So basically, this is not only the cirrus cloud, we sort of consider all the ice cloud all together, how that threshold will be. Threshold, basically, that crossover will be. So we're trying to using observations, using radio transfer modeling, say globally averaged, what number is that? So basically that eventually we wanted to get a number of that. So the data we're using is basically from CloudSat and CALIPSO. They have two very nice data set over there. One is called DARDAR. Basically, this from the UK. They using all the data to retrieve the optical depths, the effective radius of the ice content, the phase liquid content. And another data set is basically the standard from the CloudSat project. This one called 2C Ice is developed by University of Utah. So we're using the two data sets. The two data sets basically giving the same thing, the same number, the same variables, but have slightly different number. So we're using the average of that as the mean and using the difference between the two as the error, as error, basically sort of give you a sort of error estimate how much the difference will be. And because CloudSat only operated fully, day and night, fully about 4.5 years, basically using just 4 years data to do this. And here is some of the result about, say, global mean, what's the ice water or what's the optical depth, how they distributed, sort of ice cloud climatology, how that looks like. As you can imagine, say, the ITCZ, you have lots of ice over there, and the storm tracks in the mid-latitude, you have lots of ice. This is ice water content. Basically, you have lots of ice in the storm tracks over there. In the southern hemisphere, over ocean, you have lots of there too. And if you look at the vertical, so where they are, and in the tropics, this ice are very high in a very tall place. And in the mid-latitude, actually, particularly in the southern hemisphere, they're pretty low. So basically, these ones, because it's low, actually, the greenhouse effect is very small. And because very high, usually this greenhouse effect is very large because they emit long-wave radiation going out are very low. So, and also in the tropics, you can see this is the frequency of occurrence. This is the total, how much ice water distribute there. So if you look at the tropical cloud over there, the ice cloud over there, actually they are, although frequently occurring, but not a whole lot of water. What that really means is they are very thin. It's a very thin clouds. So thin clouds actually don't intercept too much solar radiation. So but they do have a lot of effect on the greenhouse effect. So basically all those ones, we have to take that into account to sort of do an estimation. And so if you look at that, in the distribution, in say the frequency distribution in the optical depths, this is optical depths. We see that is in the visible 0.55 micron wavelengths. Whenever we say optical depth, it means optical depth of that at that wavelength. And you look at that, then you say globally, most of the optical depths actually have the peak somewhere around 1. So basically, it's optical depth equal 1 have the mostly frequently occurring. And of course, because it's a skewed average, if you average that, it's a little bit bigger. And so if you see the particle, how big the particles are, because this one's also affect the albedo, how reflective the cloud are. The smaller the particle, usually the more reflective. So, and they're sort of around 30, the peak is around 30 micron. So that one, so we using all those ones actually have to put that in the radio transfer model to do estimation, how big this number, how the radiation are. Okay, then once we have that, then we have to put that in the radio transfer model to make some calculations. So one of the term I'm here using, we call that radiative forcing or radiative effect. So what really mean, the definition here is say you make a calculation either at the TOA or at the surface. You calculate how much radiation flux is going out, and you minus the one if there's no cloud, no ice cloud, everything else is staying there, all the other clouds staying there. Only take the ice cloud out, how much the flux will be. You take that flux and then take the difference. So basically you consider that is how much the ice cloud are affecting the radiation budget. So we call that, sometimes we call it radiative forcing, sometimes we call that radiative effect. And if that number is positive, we say this ice cloud is warming the Earth. If that number is negative, we say this ice cloud is cooling the Earth. So basically we're doing, using the 4 years of observed ice cloud, then put that in the radial transfer model, calculate the radial flux at a short wave and long wave, take the difference and calculate the radial forcing. And here is a little caveat put here. Because the data, either the data, because the CloudSat is in a sun-synchronous orbit, basically passing through your local place at 1 o'clock, 1:30, somewhere around 1:30, either during the day or in the evening, in the midnight. So basically, because the solar, the sun at that one is pretty high. If you're only using that time to make the calculation, you make a mistake, a big difference, because the reflection by the cloud will depend on what time, where the sun is. And you sort of biased by the time if you're only using the data. Trading that data is the cloud only happened during that time. So what we did here is we did a big assumption here. What we do is we're assuming the cloud, if we observe once, we're assuming that that cloud will stay at 24 hours. Using the same cloud, they calculate all the different solar angles, to calculate all of them, then average them together. So this is a big assumption, whether it's good or not. So it's really needed to be, later on to study using some other, means to really look at the diurnal cycle of the ice cloud, see how wrong or how right this assumption is. So that one sort of basically have to ask you to keep in mind to do this when you interpret the result. Okay, here, then we get the result. So you make the calculation, you put all the ice cloud over there and to calculate the forcing. And this basically is because the annual mean. If you do that, let's only focus on the TOA, the surface, because most of the cloud, except the polar region, the cloud basically is cooling the Earth all the time. And so cooling the surface all the time. Let's say this TOA. That means if you consider the whole Earth as a system, basically the whole Earth system is the one, whether the cloud is cooling the whole Earth system or warming it. And basically this is the annual mean. And as you can say, if you put all the ice cloud together, the warm color basically is warming the Earth. And then the warming happened the most in the tropics and the two poles. And in the mid-latitude, you occasionally see the cooling. And that reason, of course, is because the cloud, particularly in the southern hemisphere, because ice clouds actually are stated pretty low, only like 2 or 3 kilometers. The greenhouse effect is pretty small. Mostly, happening is the albedo effect. So it's basically happened like this. If you average the whole globe, so basically this is the numbers for all the ice. What they're doing for short wave, they sort of, cooling by this much. For long wave, they're warming this much. You're adding together, it's about 5 watts warming. The whole globe, annual mean, everything together. So basically that's the number we got. So, but this is not we're interested in. Well, remember, the number we're interested in is at where is the crossover. The crossover, the thinner one is warming, the thicker one is cooling. Where is the close crossover? If you're using optical depth to say it, to measure it, where the threshold is. And before looking at that number, let's try to come back to say, if you compare all the other studies, say divide all the clouds, ice clouds, into different optical depths by sort of more understandable names, say subvisual, people can say by staying there, thin ones, opaque ones, precipitating ones. If you divide that into that, say which group are doing what. And also keep in mind, we do have this probability distribution over there. So all those numbers are weighted by the probability distribution. And if you look at the subvisual ones, although these ones usually the greenhouse effect is pretty large, but they are not really too much over there, not too many, this type of clouds, so that actually the effect is pretty small. We don't even see this from the figure, and you barely can see the difference, the number, all close to 0. And the very thin ones, usually the definition of that is, below 0.3 optical depth. You have some warming and cooling together. It's a bit of warming, but the number is not really that big. And the biggest contribution actually from here is called the opaque ice cloud. Ice cloud basically is from 0.3 to 3. The reason for that, of course, is the distribution out there. Most of the ice cloud actually have that number are around there. So that's why, say, it contribute most of the warming. And if you look at the thicker ones, they basically, although they usually contribute a whole lot, but sort of cancel out the warming and the cooling together. You look at that, they're almost not really doing much. Very thick precipitating ice cloud. It's really, you can sort of even ignore it, doesn't really matter that much. So basically that's the, using the name type of different clouds and how they are affecting the whole radiation budget. And then there's the final one we wanted to show, basically, see where the crossover. So let's only look at the TOA, and let's only look at the net effect. The net effect is the black curve. You say for the very thin ones, not really doing too much. And once the optical depth reach to about 1, actually they have the largest contribution over there. And then after that, they start going down and until come to about optical depth, become 5, and they become negative. So basically when the optical depths become a little bigger than this, they start cooling. And of course, that cooling never going too much. The reason for that is, the distribution. It's not too many of that kind of cloud over there. Most of the cloud are still at optical depth 1. So basically, the answer for that question is somewhere around 5. So basically, around 5, below that is warming, and above that is cooling. So that's globally average everywhere. Of course, if you say that actually, that's if you look at the detail, then the story will be different. Basically, is that threshold, how that threshold will change depend on season and latitude. And as you can say, if you're in the winter polar region, let's say here, basically no matter what ice cloud, because there's no solar radiation come in, there's no albedo effect, everything else, no matter what ice cloud they put there, is warming. So basically that's extreme. And if you say when you have lots of sun over there, and then even very thin ones, they start cooling. So basically the 5 is a globally average and based on the observation. But if you look at the seasonal difference and also the latitudinal difference, all the stories will be different. So, but if somebody asks you, what's the globally average value, you have to come to say, oh, it's about 5. Before 5 and after 5, the effect will be different. So basically, that's the number we come up. And here we have some caveats, of course. In those calculations, we have 2 things. Actually, we sort of assumed actually we're not quite sure. One is how much liquid in the cloud. Although in the retrievals, they do give you the numbers, how much radiation, how much the liquid waters in the mixed phase cloud. But how good the retrievals are, we're still not quite sure. That's, I think for every remote sensing people, you ask them satellite-derived ice in the ice cloud, how much liquid in it, I think they cannot really give you a very confident answer. So we really don't know that yet. Another one is the diurnal cycle we just talked about. The diurnal cycle, we assumed 24 hours staying there. Whether or not that's a good one or not good one, though it's really a new house. We needed to sort of further study about that. Okay, remember that 5. Let's move on to another topic. Is the partitioning of ice and liquid precipitation. So this one's coming from actually, when I'm doing a class talking about global warming, the one the student come to ask me, so when the start warming, and they ask you per 1 degree of temperature change, warming, what's the partitioning of the liquid and ice partitioning ratio will change. So we call that the solid to total precipitation ratio, or SP ratio. Maybe later on we just call that SP ratio. Remember, that's the solid to total precipitation ratio. So warm when things getting warmer, then solid precipitation getting less, or liquid getting more. But how that will change? So we start to see, of course, you can answer to the student and say, oh, it depends. So when you say that, of course, it's like politicians answer questions. They're basically telling you nothing, depends. So, but we really don't want to stop there. So we wanted to, based on our knowledge, try to do a guessing, see how much that will be. So that's basically all the research started. And you may ask, why that's important? So we're sort of talking about 2 things, start to say why this is important. One, let's talk about in the US, in the Western US, that's the 2 regions we right now focus on. And in the Western US, actually, there's 2 big rivers in the western, the Colorado River and the Columbia River. And they said about 70% of the water is from the snowmelt. And of course, if you live in Florida, even in California, you know how important that snowmelt is for you because most of the water is from there. And another one, you say, look at the Himalayas in the plateau. And over there, actually the 5 very big rivers over there is from the glacier and the snowpack melting from there. And actually, basically, about 1.4 billion people's livelihood is depend on those melting of water. So it's really very important one. So all those glaciers and snowpack is really depend on whether it's snowing or raining. When the temperature changes, when the global warms, when that partition changes, so how this whole thing will change, how much melting water they can get is really important. And of course, right now, we really don't know too much, at least. And here is some results we sort of know so far what we sort of know. One is from models. You can, from a reanalysis, you can get all those numbers, say how much snowing, how much raining. And one is in the West, US, let's say here, about more than 50%, looks like are here in the mountains are snow. And of course, if you look at the Himalayas, also depend on where you are, and lots of snowing. And another one you can look at is some study we recently did, is we look at the occurrence frequency, not the amount. The amount we still don't know much, but we can look at the present weather report. They do tell you today is snow, today is rain, sort of visually. But using that, you can say how the ratio is on the average sense. And unfortunately, is in the US West and the Himalayas, actually the most important place, we have very few observations. So that's the problem we're facing. Then another study, sort of we say, during the warming, global temperature warms, how this frequency will change. And this is a study we recently did, is you maybe just focus on this one. You say the ratio, this one is a frequency change, not the amount change. Basically, it's during the past 40 years, you say gradually decreasing, at least over the land. Or ocean is a little different because all oceans measured by the shapes, the commercial ships. Basically, they usually have a tendency to avoid storms. So usually that number is not that trustworthy, but still you see, a significant change of decreasing during the past 40 years. And that decrease, actually, if you look at the map, and changing in the warmer place and in the high latitude, the cold place, actually, instead of decreasing, actually, you do see on the high latitude, actually, that ratio is increasing. So basically, it's not, you just say everywhere, due to warming, everywhere it's more snow, everywhere it's more rain. It doesn't really work that way. So we do have a latitudinal difference. Why that happened, we don't know, but the result is staying that way. So we can only, at this point, only report the fact. So then we come to another study. Actually, if you go on the web, you search USDA rain to snow ratio. We do have some result from the US because we have many, many years of observation. And this is one of that pop up from the website immediately. And this one is using, say, about 50 years of record to say where it's having more snow, where it's having more rain. And the red one is the snow is decreasing, the blue one is increasing, and they only look at winter. And one of the things actually we want you to focus on is instead of looking at circles, just looking where you don't have observation. You look at this region, the Rockies, and even some here, the region in the Appalachians, we really don't have much observation. So, and then if you look at here, I put another map. This one is a little funny one, is historically, what's the probability you have a white Christmas? So basically what it did is, during the later December, where you have surface snow, 1 inch of snow in the surface. So basically it's telling you in the winter where the snow is. And you can say the most snow in the West US and around here, of course, around your areas a lot too. But here, the Western US don't have much snow. You have lots of snow and you don't have much observation. But here, because of that, that's the satellite that can come to help. So basically what we said, why are we just using some satellite to do some estimate, see what we can do. This is what we're doing. We're trying to do. We first look at all this product. We have lots of product, satellite product. To start with, we are sort of say, because we are focused on the mountain regions, the US West mountain regions and the Himalayas, we are not that much confident with the passive sensors because the surface is too complicated and giving snow how much is really not that too much. We have too much confidence on that. So you say, well, let's try focus on using radars. Radar, at least the surface is not affecting that much as the passive sensors. So here we use two products here. One is from actually it's another product you put in from your department, from Norm and Tristan put all those together, is a CloudSat CPR snowfall product. Another product, that one, we're using that for snowfall. That one is not really good for rainfall because the attenuation and the wavelength the radar is not designed for heavy precipitation. But for snowfall, it's pretty good. And for another one, when we do the rain, we're using the GPM radar. The GPM radar basically designed for rain, but it's not really good for snow. The reason for that is the minimum detection is too high, either called too high or too low. Basically, it cannot really detect anything below 13 dBz. So basically, that means most of the snow. So what we do is we separate the thin of whether it's snowing or raining. We're using the first product, the CloudSat product for snowfall, using the GPM product for rainfall. So, and also, we don't have long enough record to find the long-term trend. So that's another problem because you really just don't have that observation. And what we do here, we do this. We average all the CloudSat data together. That's many years, although the latter years are all daytime only. And to find a global climate, we call that climatological mean. Say, 1 degree by 1 degree or 2 degree by 2 degree, average all the data together to find the mean. So then we're using the DPR data for about 5 years to find also the climatological mean. We're using these two means to find the ratio. Of course, we say, because we sort of say the two mean, trying to say this one are reflecting the mean, so we can plus them or minus them so that we can do the average, the ratios. And of course, there are time and really space because they're not in different, they're in a different orbit and different satellite. Actually, their timing is not really overlap. It's not really overlapping. So that's why we sort of have to use the mean to assuming we got the climatology. And of course, we have another problem is we don't have time. We don't know the time difference. We're trying to, what we do is in the mountain regions, we're trying to use an elevation. At different elevation have different ratios. The different elevation have different temperature. So we're using that to sort of convert it to temperature. Say how that temperature, when the temperature changes, how the ratio change. And here, maybe I can skip this one. Basically, why we think the DPR only do rain and CPR only do snow. So basically, this one's trying to telling that. So I'm skipping that. Basically, just trust me. CloudSat is more fitted for snow. The GPM radars more for rain. Just, if you want to come back later to that again. And then you have to sort of separate once you have either CloudSat or DPR, the GPM observation, we have to say this pixel is snow, this pixel is rain. We have to using some way to a common algorithm to separate these two. And of course, both CloudSat and DPR have their own ways to determine it, but the determination are different. So we don't want to say two products in a different way to determine random snow pixel. We want to use a common one to do that. So then what we did is we developed our own algorithm to do it. So this is how we did it. We started using many years of surface measurements, snow or rain, and we connect that to different variables, measured variables like 2-meter temperature, humidity, lapse rate, surface temperature, ocean or land. We're using all those parameters, make a lookup table. That one basically is published some years ago. That algorithm currently is also used by the GPM science team to do it, to separate the rain and snow. So basically we do a probability distribution. Say if you have 2-meter temperature like this and humidity like this, and what's the probability of it snowing or raining based on all those observations. So we do using that. And actually there's one of that is important is the lapse rate actually have a large contribution to it. Because say if the lapse rate is negative, that means you have inversion. The melting has already started above you, and even the surface is cold. Maybe you still have rain come down. So that's why we sort of using the lapse rate to it. So that's actually one of the thing we sort of concentrate on. Right now, we are also working on how the water vapor profile are changing. This one we found is also quite important. We're still working on those one too. And so whenever you start working on something using satellite, sometimes I'm doing satellite for so many years. When I want to retrieve something, I always don't have much confidence to look at my satellite retrieval. That's right and wrong. So we have to sort of look at some reference from the surface, see whether the surface observations really gave you the number. So basically with the two surface reference we're looking at, one is called the snowtail. Basically it's in a remote area. We put some instrument over there, then automatically sends the data to you. Another one is called the Global Historical Climatology Network. Basically, this is a collection of the regular conventional stations. And they do have some snow and rain measurements. So we're using those to look at how the snow look like. And this is basically in the US West, how that look like. And when you see the map, when you first see the map, let's only focus on the two. This is the mean of the snowtail, the mean of the historical data. Then you look at the two, you find, wow, they are quite different. And you sort of start to say, well, maybe the two data sets are really having problems because, even you look at the many years of average, you still get totally different number. So even the color, you see the colors are very different. So what we happen here is, and we look at, in more detail, we found out actually, if you look at, say, the average snow with elevation, we found out actually these two are quite consistently going on the same line. Basically, say, the higher the elevation, you have more snow. And most of the snow in the stations are in the valleys, and most of the snow in the snowtail actually is in the top, in the peak of the mountains. So that actually, although these two are very close, and here we're looking at the pairs, if even the horizontal distance of those two stations are very close, but if the elevation different, they have very, very different snow together. So we sort of decide to combine these two to make a great average value instead of just using one station. And we think the big difference, both of them actually quite good, and the big difference between the two is due to their elevation. And if you look at the rain, the same thing, the rain, the dependence on elevation is much small. And we sort of, at this point, we didn't even think too much about that yet, although we see some negative correlation. But, if you look at the two nearby stations, you really don't see much pattern of it. So basically, the rain is almost no dependence. If you see some dependence, is the rain getting less and less going up, and the snow getting more and more above. And so once we have that, first using the snow, using the surface observation, see what's the rates. When the elevation goes, what's the ratio? What's the snow, what's the precipitation ratio look like? And that's from the mountains. If you only looking using the point measurements without average to the whole thing, and then you figure out what is something, you draw a line somewhere right here. It's about 30% per kilometer. Basically, is every kilometer going up, the ratio of snow to total precipitation will be decreased, or will be increased about 3%, 30%. And if you do 1 degree by 1 degree mean, using the same data, do 1 degree by 1 degree mean, you figure out that will become about 24% or 25%. So this one is more comparable, should be comparable to the satellite, because satellite, we cannot really do point to point. We have to average our area. The minimum we can do is about 1 degree by 1 degree. So this number is more like the satellite can tell you. And then, once we know the bottom line, that's the number you should get using satellite. So you're really using satellite to do. The satellite, you don't have to be in the mountains. You can do the whole area of the Western US. And we did all those ones. So you get, quite scattered. You really, numbers quite scattered, but you still can, draw a line like this. That one is about 28% per kilometer. Basically, what it's giving you is you're going up every kilometer. It's the ratio of precipitation of snow to total precipitation is getting lower, is getting increased about 28%. It's quite close to the surface measurements. So that one really give us quite confidence. So the satellite is really doing pretty good. And we sort of explain here using one slide, trying to explain why this ratio are rather doing good. Actually, it's doing much better than you only look at the snow or the rain measurements. The reason for that is in the mountain areas, the biggest problem for the retrieval is the blind zone. Basically, the space radar cannot really see the surface. They basically can only see it's about 1.5 kilometer and above. So what you use using this 1.5 kilometer altitude level to guess what the surface precipitation is. And actually in this place, because of the orographic effect, most of the profiles are having something like this, downward increase. And what we found out is both the CloudSat and the DPR, the GPM DPR, are underestimating compared to the snowtail and compared to the climatology. It's about, about 50% less. Basically, this is not because the algorithm is wrong. It's because they're really not seeing the surface. They're seeing the 1.5 kilometer. And if both of them are sort of, have the same problem, decreasing less, then you take the ratio, the SP ratio actually have really a much less effect. So then if you do the ratio, doing the ratio, actually your problem due to the orographic effect during the blind zone actually is much reduced. So the ratio is much reliable. So after we got that, we sort of going to a more difficult place, go to the Himalayas to do that. The Himalayas basically is really lots of large in mountains, very high. And if you look at the place is about 5 kilometer and above, a lot of those places. So what we did is doing this, first to compare using CloudSat and DPR to look at the mean, how much we get climatology using several years of data. Compare that to one of that, this one is the surface rain gauge, one of the data set done by a Japanese colleague. They sort of put those together. You see the patterns pretty close. And also you can look at the ERA5, and here the patterns are okay, but you have to pay attention to the scale. Basically, we have to double the scale in order to match this. That means the ERA5, the total precipitation is about twice of the radar and surface gauge are saying. And then we do the ratio. So basically here is the SP ratio, is the snow to total precipitation ratio we get. So it's come to this pattern. Actually, this place is very interesting. And actually somewhere around here, we call that several of the mountains over here. Actually, the most snow are falling during summer because the monsoon bring a lot of water vapor here, and here is very cold, very tall place, and most of the snow on the top actually is during the summer seasons. So basically something like this, the pattern. And if you look at the dependence, and here just only focus on this one, basically we're only interested in this slope of that change with elevation. So we got a number around about 23. I could say 25 or something. Oh, doesn't really matter, 23, 25. We got this number actually very close to the Western US number. So basically that's, also gives some more confidence to say this one is doing the ratio to look at over the mountains and give you the number, very consistent at different locations and also with the surface, from 25 to 30, somewhere around there. Okay, I think we're almost around out of time. So basically today, what I talked about, I wanted you to remember 2 numbers. The one number is the one we just talked. Say over the mountains, if you measure the ratio of snow versus total precipitation, that ratio is increasing over the mountains every kilometer about 25% increase. So go up 1 kilometer is 25% of ratio are increasing. So that one, if you're assuming the lapse rate is about 6.5 on average, and then that translated to 4%. That means you decrease the temperature about 1 degree Celsius, you increase the probability of snow for 4%. Or you can do the opposite. You increase the temperature by 1 degree, then you decrease the ratio about 4%. And then another number is we talked about earlier is 5. That means the crossover, the threshold for cloud ice to warming the earth or cooling the earth is about 5. So if today, of course, we have lots of caveats over there, lots of problems. And of course, if you can, going back, take home about the 2 numbers, one is a 4, one is a 5. If you can remember that, then my 45 minutes talk maybe is worth it. Okay, thank you very much. I'm ready to take questions.
Thank you. Lots of little virtual applause in the chat. I open the floor to grad students and early career folks if they want to ask a question. So Julie and I will be monitoring the chat. Just go ahead and raise your hand. Give people a minute. And Julia, if you see anyone, you can go ahead and unmute and call them too. Okay, go ahead. It looks like a question from John.
Okay, thank you for your great presentations. So my question is about your plans for diurnal cycles in the futures.
Okay. Okay. The one thing actually we really wanted to look at, maybe using different satellite to look at the ice cloud, just maybe even the ice water or whatever amount, even ice cloud amount, whether or not they have a dominant diurnal cycle. Of course, that also depends on the locations. So if we taking into that account, how much the difference the number will be. Because right now, we only get the observations only at like 1:30, either during the day or 1:30 in the night. In the night, you don't never have solar radiation. But 1:30, the sun is very high, and your albedo effect is pretty large. If you're only using that, definitely your calculation will be biased. So then, right now we did another extreme. We're assuming the cloud will stay there for 24 hours to calculate all the times. Then whether that's a good assumption, or even that is better than just using the 131, 130 is really up to debate. We really don't know how right or how wrong it is.
Okay, thank you.
Okay.
Yeah, thanks for that good question. I want to open up to anybody, but grad students are still encouraged to ask questions if they have any. You can just go ahead and raise your hand and we'll be monitoring in the chat. Yeah, go ahead, Angela.
I have a question about your optical depth plots. I appreciate it you went into the seasonality, but I was wondering if you had looked at also the interannual variability. Does it vary year to year very much?
No, not there yet. Not there yet. Actually, we're using the CloudSat, and basically they really only had a 4 full year of observation. Mm-hmm. After that, it become daytime only. If we use that, we do another skewing of the average. So we really need more observation, similar kind of observation. The future, right now they call it AOS or ACCP, whatever that number is. But we have to wait until 10 years until launch, and after 10 years, wait another 50 years to get a interannual variability. So I think the next generation, particularly the current students, maybe current students will have the opportunity, to study that. But for us, we're really trying to squeeze whatever we can do to look at the mean. Really, I think that's mean. After 4 years, I think that's mean. So basically, really, we are still in that stage.
Thank you.
Okay, thank you.
Thanks. Looks like there's a question from Rudra. Go ahead.
Yeah. Hey, Professor, it was a very interesting talk. And my question is related to the same slide that you are currently presenting. It is more like an weather event that if we are having an extratropical cyclone in the Arctic or Antarctic region, then maybe the threshold will be changed, like the warming to cooling threshold, and how big that could be.
That can change a whole lot. Actually, right now we're sort of averaging everything, become this number. And say, if you have a large system it really depends on where they are. And the cooling the albedo effect is basically really depend on how much water or how big the particle, how small the particle is. And the warming effect actually depends on several factors. One of the big factors is where the cloud is. If the cloud is very close to the surface, you really don't have much warming. And then you mostly, you have to put the cloud in a very high place, the ice cloud. That's why, say, when you have the tropical cloud, and let's say put somewhere here, with this cloud, it's really warming a whole lot. So that's basically the long wave radiation from here going out. It's very small, and the intercept the very warm from the surface basically puts that radiation back. So that's why they're depend on where you put it. So very system as you said, depend on the system. So that's why we want to use observations, average everything. We think the average, after you're averaging, you are getting the mean state of the climatology. So using that mean state, trying to figure out what's cooling or what's warming.
Okay, thank you.
Okay.
Thank you. Other questions? There's time for a couple more if people have them. One more. I might ask one. If you go to the partitioning slides, maybe the slope slide of the probability of snow over total precipitation. So I just had a curiosity about these trends. If you were to, instead of looking at all of them, if you were to look at only the most extreme impactful events, do you have a feeling of how this might change? Possibly just knowing kind of what systems are predisposed to depositing more snowfall in the mountainous regions or precipitation in general.
Yeah, that's really very good question. It really depends on the system itself. Say, for now, we're really looking at using the algorithm I sort of using. It's sort of basically averaged everything. And if you look at the individual system, depending on what system you're looking at, that number can change, that threshold can change several degrees. Several degrees is a whole lot. If you look at my figure here, let me show this figure here. You see, on average, if you do the average, the transition is really occurring, like I say, about 5 degree window. If you switch that like 2-3 degrees, you basically say it's switching from 10% to 80%. So like it going that way. So that one, how the individual system, how they, even some of the location maybe, how the atmospheric structure are changing to affecting the phase change, are really big, a big thing I think need to sort of figure out. Hopefully you can do some more study on that and trying to figure it out. So that's really a very important one, I think.
Okay, yeah, thanks. This is a great figure, and that's like, very useful. So yeah, I appreciate it.
Okay.
Yeah. Other questions from folks? If not, we'll wrap up. Everybody can virtually clap for our speaker. Thank you so much, Professor Liu, again, for joining us and taking the time. It was a really interesting talk.
Okay, thank you very much for coming, everybody. I think I'll see some of you tomorrow. Okay.
Yeah, great. Thanks, everyone.
Okay, bye.
See you tomorrow.
Okay.